Hello everyone, welcome to the lecture number 34 of this NPTEL lecture series on charging infrastructure. In the last lecture we have discussed about switching losses, and in this lecture we will carry forward our discussion related to that, and we will see and understand the concept of soft switching. Now if you look very carefully, we have defined our circuit to be something like having a switch and a diode, and it is actually supplying the constant current load. What it means is it is actually supplying a, what you can say, inductor, and let's say either R, or you can say the parallel combination of R and C as a load. So this is what we have assumed. This particular circuit we have assumed to be something which is, here the output is actually I naught with certain ripple over it, and this is RL, and this is C, and this is L. So this we can assume that, since if we assume the ripple component is very minimal, so we can say that our system was something like this. And there we have seen that, we have the constant current. We can determine the load as drawing a constant current at the output of the combination of switch and the diode bridge. So then we have seen that we have derived our switching loss for this particular scenario, and we have seen our P switching is nothing but V in times I naught. V in is the voltage which is been applied across the bridge comprises of switch and the diode, and the current which is coming out of that half bridge multiplied by the period during which the switch is turning on, which is nothing but T switch on, which is nothing but a combination of T rise time of current and fall time of voltage, plus the loss which will be occurring during the switch off time, which is nothing but again V in I naught by 2 times T switch off. Then T switch off is the period during which my voltage rises up across the device, across the switch S1, and time during which the current also falls down. So we have the T switch on and T switch off. So we can write T switch on to be nothing but equal to TRI plus TFV, and we can also write T switch off is nothing but the rise time of voltage plus fall time of current, and the switching frequency FSW. And this is primarily because we have assumed that we have connected an inductor at the output of this particular bridge. However, in case when we have just the resistive load, this term will not be, this switching loss, the loss which is occurring due to this transition will not be this much, will be V in I naught by 6 times in case when we have resistive load. However, in this particular case, since we are only bothered about the voltage source converters, and most of the voltage source converter have the inductor kept at its pole of their bridges, we have only considered this particular case. Here if we look very carefully, the switching loss, it depends upon the, obviously, the switching frequency, the number of times the transition is happening, the blocking voltage of the device, the voltage which it will block once it will be off, and the voltage which will be coming from the non-zero value to the zero value when it is turning on. So that's a blocking voltage, and the current which will be flowing through a switch when it is on, and finally the time required for turning on and turning off of these devices. So our switching loss depends upon that. Now let us see how our system look like if we just take our switching transitions we have taken over here. Now if you look very carefully, the overlapping period, the period during which the current is rising and voltage is falling, is the time during which you will actually be having some losses which is happening across the device, and that is during the T switch on period and T switch off period. So we can say that in this particular thing, during T switch on period and T switch off period, that means you can say the instance during which this voltage and currents are overlapping, during this period there are two things which is happening. First is obviously the loss, and this loss we know that is nothing but V in I naught by 2 T switch on plus T switch off and FSW, that is happening during this switching period, during T switch on and T switch off period. So during this thing following takes place. So it's the losses. Now these losses lead to reduced efficiency, and this will also, in other words, it limits the switching frequency. If you wanted to have the improved efficiency, you must limit your switching frequency. So this is the first thing which is happening. The losses, which is one of the important consideration. Let's say if you are switching at very high switching frequency, because you go for switching higher switching frequency, so that your sizes of your passives comes down, because sizes of passives are inversely proportional to frequencies, switching frequencies. So that losses is one thing which is happening. The second thing which is another important thing which is happening in the system. Whatever the circuit we have something like this system. This is D, this is S1, and this was going I naught at the output. So here what we have seen, that during when you are turning on this S1 switch, during this period the current through the S1 switch start flowing through the S1 switch. Suddenly, when the moment to turn on the S1 switch, the current which was, I mean, previous to that it was going through this, will then shift to the S1 switch. And the moment at that point, what we will see is that if you mark this at the output of this bridge, that A point, and let's say this is N point, then what we will see is that the VAN, if you draw this VAN on this particular thing, what you see is that the VAN at, I mean, the VAN will start having V in voltage will come at VAN. So that means this VAN voltage goes from 0 initially, because when the diode was on it was 0. So this VAN actually goes from 0 to V in. There you do not have any control. That happens how fast you are turning on this S1 switch. So during this time you have certainly certain delta V by delta T which is appearing at the output of this bridge between point A and N. And this delta V by T, if you look very carefully, this is actually nothing but, mostly it is V in, and this delta T means how fast the switch S1 is getting on. So this has good amount of delta V by dt, and you can say, in other words, you can say that it has good amount of dV by dt which is coming at the output of the bridge. At the same time we also have good amount of di by dt, because suddenly the current was not there in the upper branch, and suddenly when you turn on the S1 switch, suddenly, I mean, which was flowing through the diode will suddenly move to the S1 switch. So it will also have a good amount of di dt and some small period of time. So it will also have some delta I by dt. Previously it was 0 current, now it is I naught current. So it has good amount of di dt. So we can say that here we have this di dt, and that actually this there is good amount of electromagnetic interference due to dvdt and didt. And this, on one hand, you wanted to have this switching T switch on to be as small as possible, such that your switching loss is small. On the other hand, the moment you go for a smaller T switch on, that means you have a smaller TRI and TFE. So when you have TRI and TFE, then your these DT values in both the things become very small, and that's when you have good amount of or very high dVdt and dIdts which will be imposing at the output terminal of your half bridge, or the bridge comprise, in this case bridge comprises of S1 and D diode. This is also another thing which is taking place, and because of high, or you can say uncontrolled, because of high dVdt and dIdt, there are dVdt related problems, there are dVdt and dIdt related problems. Now those problems are, those problems are like false turn-ons which takes place because of high dVdt, and because of high dIdt you have, in gate to source voltages you have sudden oscillations which appears, and that may damage your devices. You may take your devices to operate at certain unsafe region of operation. So these are the problems which we see, which happens whenever we have during T switch on and T switch off period. And to reduce P switching or the loss during switching, the T switch off and T switch on time need to be reduced. However, it leads to higher DIDT and DVDTs. And because of higher DIDT, DVDTs, your EMI performance or electromagnetic interference performance reduces, and you have certain DVDT, DIDT related problems appear in the circuit, which is nothing but false turn on and oscillations on your gate to source voltages. So DVDT actually lead to false turn on of the devices, and DIDT actually leads to oscillations in your gate to source voltages. So these are the problems which we have. So what we want to have, on one hand we wanted to go to high switching frequency such that size of passive goes down. On the other hand, we want our switching losses to be as minimal as possible, because high switching, since you are going to high switching frequency, that means this is fairly good amount of switching frequency. V in and I naught you cannot change, because that is not in your control, that is given in the specification. So what is in your control is the time duration during which T switch on and T switch off. That is something which as of now you have the control. Now since you have the control on these two things, you would like to have these two numbers to be as small as possible. But the moment to go for this number to be as small as possible, that means the transition during which the current switches and the transition during which the voltage switches will actually be very less. And since those transition, the time duration is very less, the DVDTs and DIDTs are very high, and because of that there are problems related to high DIDTs and DVDTs, like EMI performance get problematic, or you have false turn-ons of the devices, and that lead to the short circuit and the oscillations in your gate to source voltages. So to avoid this thing, people start using a method by which they can eliminate, or they can at least reduce the impact of these particular effects, and that particular phenomenon is called the soft switching. Now before I start going to that, let me also say, so DVDT actually leads to false turn-ons or false turn on of the devices, because your voltages on the gate to source will go above the threshold voltage when the switch is off and other switch is turning on. That's when you have false turn on of the switch which is off. So both the switches are on in the half bridge, and then that leads to the false turn on, and DIDT actually lead to oscillations in gate to source voltages. So again, these are things which we are not going too much in details. Primarily these are the problems which occurs because of these things. So let us see how we can avoid these things. Now to go ahead with this, we have till now we have been discussing converters like this, where we have a switch S1 and D connected in this fashion, and it is supplying to the I naught current. That we will, in more generalized manner, we can define this to be a two switches having the if let's say these two switches are realized using MOSFET, then they are the body diodes. If they are realized using IGBT, then they are the freewheeling diodes to those, so that we can get the fundamental building block of any, because this particular structure is fundamental building block of any voltage source converter, and having the inductor connected at the pole. So it's a fundamental building block of any power electronic converter. Now we can, so for easiness, let us also take a system to be something like this, where let us take, we are using a MOSFET S1, this is S2, let us say this is V in, this is, let's say, D1, D2, and since we have a MOSFET We will also have, every MOSFET has a parasitic output capacitance, and let us define this as C1 and C2, and this is actually supplying to the output current I naught, I mean to the load I naught, and this C1 and C2 are the output capacitance of MOSFETs S1 and S2. So we will now, from now on, we will consider this particular structure, and we will try to see the concept of soft switching. Okay, before understanding the how we can get the soft switching in this particular conventional building block of any voltage source converter, now let's consider this particular converter architecture and these waveforms we have already drawn in last class while discussing the switching laws concept. So in this, so whenever we are turning on this S1 switch, what is happening is, before, when S1 was off, the current was actually flowing through the body diode of D2, or maybe if you turn on the S2 switch, so channel of S2 switch, it is flowing through that, through in this way it is flowing, and then at that point my current through this S1 switch is 0, because the entire current is going through this loop. Now during that time, and since this switch is on, the voltage across bottom switch is 0, so the voltage at VAN, we can say that it is nothing but a 0 voltage, and the entire voltage is coming across the switch S1, which is what, which is nothing but V in switch S1, which is coming across this one. Similarly, on the other side, when it was off, when switch was given off signal, during the off signal, the current will start shifting from the S1 switch to the bottom switch. Let's say bottom switch, through the diode D2, it will start going through the diode D2. Since the switch current is going to the D2, so voltage across D2 will start falling, as a result of which the voltage across S1 will start rising up, and because the moment it reaches to V in voltage, the current which was somewhat it was going through here will now be going to 0 afterwards, and the current will then be fully going through the diode D2. During this time, if we look very carefully here, during when it is turning off, the I current is going from I naught, some non-zero value, to 0 value, and voltage across VS1 is going from this 0 value to the non-zero value. While during turn on period of S1 switch, the current through the S1 switch is going from 0 value to non-zero value, and voltage across the switch goes from non-zero value to the 0 value. Now if we look, the power loss is happening in T switch on and T switch off period, where the current rise or fall and voltage rise or fall through switches are overlapping. If we are avoiding this overlapping, then we can reduce the switching loss nearly to 0. Now let us see how we can do that, and let us see during turn on period of S1. Since the I naught is 0 beforehand, if I can somehow ensure that this voltage goes to 0, before the current start rising, then I can ensure there is no power loss in during this time, that I can ensure. Similarly, if I can somehow ensure, if I delay my I naught rising in such a manner that after it occurs after the voltage falls down, then also I can avoid having any overlapping. So you can say I naught I am delaying, and V you can say that I am leading, or you can say somehow I am ensuring this falling is happening before the current start rising. Somehow, there could be many means. You can connect some external circuits, or you can, by the operation of the converter, it may happen. So during that time I can do that. Similarly, during turn off case, if I can somehow ensure, I can make sure current goes to 0 before voltage start rising, that I can get it by either leading, or you can say that pushing the current fall before the voltage start rising. If I can ensure that, then I can avoid having any overlapping. Similarly, I can delay my voltage rising after my current falls down, that also I can do. That can also avoid this overlapping of this rising current and falling voltages, or falling current and rising voltages, and that's when I can avoid this T switch on period and T switch off period. and since if I avoid T switch on period and T switch off period, the losses, and it will also help in reducing sharp DVDT DIDT, as the voltage or current transitions are now governed by the arrangements we have done to make the voltage fall to 0 before the current rises during turn on, and making the current falls to 0 before the voltage rises during turn off. I can avoid. So we can write two important points out of this. The first point is, during turn on, if somehow we ensure that voltage falls to 0 before current start rising, then the T switch on period can be avoided, or you can say the overlapping of current rise and voltage fall. Can be avoided. Okay, can be avoided, and that will lead to, you can say that actually this will give the P switch during on to be equal to 0. So we can say that if during turn on, if I can somehow ensure my voltage goes to 0 before my current rises, we can completely eliminate the T switching period, which is overlapping of current rise and you can say the voltage falling, and that is when we can ensure that there is no switching loss which is happening during turn on. Now this particular scenario, since we are ensuring the voltage goes to 0 before current rises, is called as the 0 voltage switching, and it is abbreviated as ZVS, since we are switching with the 0 voltage, and that primarily occurs during turn on, and because during turn off the voltage is already 0. So there is, I mean, you do not have to bother about having ZVS during turn off case, because before, when you are going for turn off case, your voltage was already 0 and then you are going to some non-zero voltage coming across it. So voltage was already 0. Here we are somehow ensuring that voltage goes to 0 before current start rising. Similarly, we can, on the same line, we can write down during turn off case, if somehow we ensure that current goes to 0 before, if current goes to 0 before voltage start rising, then the T switch off, which is nothing but overlapping, you can overlapping and voltage rise can be avoided, and this will lead to P switch off to be equal to 0, and that particular scenario is called as a 0 current switching, and it is abbreviated as ZCS, and this primarily happens, this 0 voltage switching happens during turn on, it is important, and this is happening during turn off, because during that time we are making those things to goes to 0. Now in this particular, since we are having the voltage source converters having driven by the voltage source and having kind of constant current at its terminal, because most of the time at the output of the terminals of half bridge you are connecting huge inductor followed by load or followed by source. So you are actually drawing the constant current from the output of half bridge. So now conventionally this particular converter structure, because of the operation of the converter, it has the scenarios in which at least one of the device goes to the 0 voltage switching during turn on, and that is when we achieve ZVS operation, and we can say during that transition our T switch on is nearly 0, and that is when we can have a a soft switching scenario. So let us take our system to be half bridge. Made up of let us take whether we can achieve our ZVS and ZCS in our conventional half bridges or not, and without adding any additional circuitry. So let us take, see this is our C, this is S1, this is S2, this is D1, D2, and the capacitance, output capacitance C1 and C2, and this is actually driven by this current source, something like this. Now in this thing we know that since they are the conventional half bridges, S1 and S2 are complementary to each other. That means when S1 is on, S2 is off, and when S2 is on, S1 is off. Both can be off, but both cannot be on simultaneously. So we have to provide, a dead time, and there is dead time during transitioning or during transition from off to on. In both the cases, from off to on, there will be dead time will be provided, and during the dead time both the switches will be given 0 signal. So what we have is we have S1 equal to 1, and during that time S2 equal to 0, and then we have S1 equal to 0, and since because of the operation we will make S1 S2 equal to 1. But going from this transition to this transition, we will insert some dead time in between them, such that we will allow our switch to turn off completely before the other switch turns on. Otherwise, if the switch, let's say we are going from S1 switch to S2 switch, so we have turned off our S1 switch and we are now turning on our S2 switch. If S1 switch does not turns off fully, then there will be short circuit of this voltage source. So now let us see during this transition whether we can get the ZVS or whether we can get GCS, but here we do not connect any other circuitry externally. How this conventional half bridge, in what scenarios it will achieve, because if you look very carefully, there are 4 instances. One instance is when S1 is turning on, another instance is when S1 is turning off or S1 is turned off, you can say it is turned on. Another instances will be S2 is turned on, and then the other one will be S2 is turned off case. There are only 4 transition which takes place in this conventional, or you can say the half bridge, which is one of the building block of any voltage source fed power converter. So let us take one of the instances when my S1 is turned off, and after turning off my S1 I will go to turning on the S2 switch. So S1 is turned off. That means we can say that S1 goes from on to off. Now let us see how our system look like. So since my S1 is going from on to off, so initially, so since S1 is on, the current is actually going from here to switch S1 and going here and then coming back here, and the S2 was off, and that's when my S2 is actually blocking V in voltage of this MOSFET. The output capacitance of S2 MOSFET, which is nothing but C2, is actually blocking V in voltage. Now after this, what happens is that after this the dead time occur, during which what happens is that you have removed the pulse from the S1, from the gate to source of S1 switch. That is when what happens is that we will see what happens during the dead time. That time S1 is off and S2 is also off, both are off during this time. So during this time, in order to ensure the current remains I naught, what happens is that, see, now there is no channel which has been formed in S1 because you have now removed the gate to source voltage, or make the gate to source voltage corresponding to turning off of the devices. During this time my S1 will also be off, the channel which was conducting will no longer exist, and there is no pathway from where the current can flow through S1 switch and S2 switch. So this is D1, D2, and now what happens is this, we all have as C1 and we have C2, and it is actually giving. Now during this time, since this current has to be there, so we must ensure that this current I naught still persists, and during this time what you will see is that there is a current, some current is actually flowing through this C1 and flowing like this, some current will be flowing through C2, and some current is coming over here and some current goes over here. Now this, let us say this is IC1, IC2, so we can say that IC1 plus IC2 is equals to nothing but I naught current, which is going at there. And if you look very carefully, the voltage which was there across C1 is actually now, since the current is coming out of the capacitor C2, so the capacitor C2 is discharging, we can say C2 is discharging, and because of the current direction C1 is charging. So C2 and C2 is discharging, C1 is charging, and so that means we can say that Vc2 is reducing and Vc1 voltage is increasing, and that is when we will see that. So in during the dead time, what happens is that this voltage will keep on reducing, which was at V in, which was keep on reducing, this voltage will keep on increasing, and what we will see that now, since this will keep on going until the voltage across this becomes 0 and the voltage across this becomes V in, and that is when, since the voltage across this is 0, this diode D2 gets forward bias, and that is when the current will now start flowing through the D2. So I naught is nothing but equal to ID2. Entire current will be going through the diode D2, and Vc2 is equal to 0, Vc1 is equals to V in, and we can say that since the entire current is going through the D2, we can say that the Vs2 is actually nearly equal to 0 if we assume the forward voltage of the diode is negligible. So we can say voltage across the switch S2 is actually 0. Now if you look very carefully, we have not given a turn on pulse to switch S2, we have only removed the pulse from S1 switch. So we have here, we have S1 switch is on, and during this time my S2 is off, already it is off. Then you have removed the pulse from the S1 switch, that is when the S1 is off and S2 is on, and that is a dead time. In that time what happens, the C2 gets discharged fully, is getting discharged, and C1 is getting charged, and this will continue until the voltage across C1 reaches V in, because beyond that it cannot go, and voltage of Vc2 becomes 0, and that is when you will see that since the voltage across C2 is 0, the diode D2 will start conducting, and that is when the voltage across Vs2 becomes 0, and the current is actually flowing through the ID2. And now we have understood during turn on case, if we somehow make the voltage goes to 0 before the current start rising through the device, we will get the 0 voltage switching. So here we have made our voltage goes to 0, and now when we give pulse to S2 switch to turn on the channel, to form the channel through S2 switch, the device will achieve the 0 voltage switching, and which will actually have negligible loss, or you can say 0 loss, due to the overlapping of voltage falling and current rising, and we will get the 0 voltage switching off during this time. So now what will happen is that at this point we can also say one more thing here. Since this I naught current is there, we can say that the voltage, or you can say the voltage VAN voltage, if I write VAN voltage, here the VAN in this case was, since the S1 was on, it is nothing but V in. Here the VAN voltage is actually reducing, or is reducing with Vc2, and here VAN is actually 0. So we can say that our VAN goes from V in to V0, and if we look very carefully, the rate with which this voltage is falling is not dependent on how fast you are turning off your S1 switch. It only depends upon this capacitance C1 and C2 and this current I naught. So we can say that in this case my dVdt is actually nothing but limited. This dVdt is limited, and this value we can get is a dVdt to be nothing but equal to I naught by C1 plus C2. It only depends upon the external current which is flowing out of the half bridge and the output capacitance of the devices S1 and S2. Now after this, so what we have done, we have ensured our Vs2 goes to 0 and the dVdt is limited, which is given by C1 plus C2 by I naught. However, this capacitance are non-linear capacitance, it depends upon the voltage to across these devices. So but they are limited, they are, they are not depends upon how fast you are turning on and turning off S1 and S2 switch. I mean, it is independent of your gate to source circuit or your gate to source loop. So what we have got Vs2 goes to 0, we have got that, and we have limited dVdt, which actually lead to good EMI performance, because you will not find any sharp edges or any oscillations during the across the voltages of these devices. So what we have is we have Vs2 equal to 0, and when you are now turning on S2 after the voltage across Vs2 goes to 0, so what you will get is, you will get when S2 is on, turning on S2 means you are giving gate pulse to S2, some gate pulse to S2. During that time, if this is my I naught, so I can say the current will now start flowing through the S2 switch. However, the voltage across this was already Vs2 is actually equal to 0, and this current we can say Is2 is nothing but equal to I naught. So we can get P switch on to be equal to 0. In order to ensure this is 0, we must ensure that sufficient dead time is provided such that Vc2 goes to 0, and simultaneously Vc1 goes to V in, and here it is V in voltage which will be coming over here. So we can get P switch on equal to 0, and along with that we have limited dVdt, which is nothing but I naught by C1 plus C2. And if you look very carefully in this case, since we are ensuring our C1 is charging to V in voltage from 0 voltage, and C2 is discharging from V in voltage to 0. Thus we can say that the energy which is there in this one is nothing but energy in capacitances is nothing but half C1 V in square plus half C2 V in square. And if we can say energy associated with I naught flowing through inductor L, because generally this indicates we have at the output of this bridge we have L and then some C R L, or you can say here we can also have load, or we can also have any voltage source or RL whatever. So this L is there, and which is having the I naught. This is S1, this is S2, this is the actual circuit. This was the derived circuit we have got here, but this is the actual circuit. So we can say the energy associated, because since I naught is flowing through L, we can say it is half L I naught square, and the Vc2 goes to 0 and Vc1 goes to V in whenever the S1 turns off, and there during the dead time when S2 is turning on, and after which S2 is turning on. So during this time, this energy whatever is there must be sufficient, that this energy whatever which is there because of changing the states of C1 and C2, this particular energy must be greater than this. So we can say the necessary condition is my L I naught square must be greater than C1 V in square plus C2 V in square. This is the necessary condition, and this particular condition is your this is the necessary condition, then this is the required condition. That means the necessary condition, this energy associated or energy with the inductor must be sufficient enough to take out the required charges from C1 and C2 in such a manner that the C1 goes from 0 volt to V in voltage, and C2 goes from V in voltage to 0 voltage. This much energy has to be taken out by this current which will be flowing through inductor L. So that's when that is the necessary condition. However, once the necessary condition is met, then one must ensure there must be required that time is there such that the voltage across these two gets to 0. So this becomes the required condition, or you can say that the condition which is a sufficient condition for the voltage across these devices to goes to 0, or you can say that ZVS of switch S2. So we can say that here in this particular case we have ZVS of switch S2 we are having during turn on of S2. So we will get our this thing here. So this is the first condition we have seen, that out of 4 condition, in one of the condition we are getting ZVS. Now when the next thing is happening, when S1 is turning on, that means going from off to on, during that period what happens is that S1 is off. Since S1 is off, we can say that the current was going through S2 because S2 is on. If S1 is off, S2 is on, so current is going through here, and we can say that the voltage across this is nothing but Vs1 equal to V in. Now what happens, you are now turning off. So now you will do S1 is on, or you can say S1 is off and S2 is also off. That means during that time. So here we can also see the turning off of S2 as well. So during that time, since you have turn off your S2 switch, so channel is not been there because you have removed the gate pulse. So now what happens is that the current, if let's say D1 C1 D2 C2, so current will now, because in order to find the path through the circuit, it will now start flowing through switch D2, and we can say I naught is nothing but ID2. Here the I naught is nothing but equal to IS2, and because of this thing, the here we can say here it is 0, and here still it is 0 because the current is going through there, and here it is still V in voltage. So this is my dead time, and this is the dead time. You are now giving pulse to S1 switch. So now what you are doing is, you are now S1 is on and S2 is off. So now during this time what happens, because there is no other way, because of the direction of the current will start flowing through the diode D2. There is no way by which I will reduce this capacitance voltage, because the current is going through the diode D2. So D2 is forward bias, the voltage of C2 is nearly 0. Since the voltage across C2 is 0, since we have V in voltage across here, so that V in will be coming across the C1. So there is no way by which we will be able to discharge capacitor C1 voltage from V into 0 before the gate pulse to S1 is given to turn on the S1. So that's why when we gave pulse to S1 to turn it on, the C1 will discharge through the switch S1, and then the voltage across C1 will go to 0, and that's when we can say we have now suddenly the channel is been formed, and the current will start flowing through this, and that's when the voltage across this becomes 0, and the voltage across this becomes V in, and this voltage which was there in C1 will now actually get discharged through this S1 switch. So that extra charge which was there in C1 will also get discharged through this channel, and that's when we have good amount of losses in this one. So here we can say that I naught is nothing but equal to IS1, and some non-zero T switch on is there on, or we can say some non-zero, P switch on will be there. So we can say that we have, since now as in the case when S2 is turning on, we have 0 voltage switching or ZVS of switch S2. So we can say that there we have short switching because we were softly turning on the S2 during turn on, because we are softly turning on the S2, because we have make sure the VS2 goes to 0, voltage across S2 goes to 0, and the transition is soft, because you can say transition is limited by the output current and the capacitance of these devices, so that you can say that we have softly turning on the S2 switch. And here we can say, since the some non-zero P switch on is there and high DVDT is there, high DVDT, because you have suddenly formed the channel whenever it was blocking the voltage V in, and you have suddenly turned on, you have suddenly created the channel, and the entire voltage across the C1 get discharged to S1 switch, and the another V in will start appearing across C2, and for that it will again take extra current through the channel of the S1 itself to charge to V in. The C2 will get charged to V in by taking additional current from the V in voltage itself from here itself. And so here if we write VAN voltage, it is 0. Here again it is VAN voltage is equals to 0. If we write VAN here, voltage 0, and here if we write here VAN, it suddenly goes to V in. There it was slowly going to 0 voltage. Here it has gone suddenly. You can say that this transition goes from this VN voltage goes from 0 to V in is only depends upon how fast you are creating the channel in this switch S1. That's when you can say it all depends upon how fast is your gate drive circuit is, and the time period of going from V voltage of Vn goes from 0 to V will only depending upon the gate to source circuit. I mean how fast the gate to source start forms the channel, and the current which was flowing through the D2 moves to the channel S1. It only depends upon that. So high DVDT, and you can say some non-zero power loss, and this system is called as this type of switching is called as the hard switching. So hard switching of S1 we can say. So what we have seen, if we take this particular circuit, then we can say that I mean in this circuit we can say that S1 turns on with hard switching, we can say that S2 turns on with soft switching, we can say, which is nothing but a ZVS we will get. So we can say that the S1 turns on with hard switching and S2 turns on with soft switching, which is nothing but the ZVS operation we get. However, if we think about turn off case, we would like to have the current goes to 0 before my voltage start rising up during the turn off case. During the turn off case, in this kind of circuit is quite difficult because we are not adding any additional circuit to it. Since we have connected an inductor at the output of the current, so we can say that we have the current which is kind of constant current coming out of this half bridge. So there it is difficult to make the current goes to 0 since we have inductor coming out of it. So that is why in this kind of circuit we can only have the soft switching during one of the turning on of one of the switches, while we will have the hard switching when we are turning on with the other switch. We can say that ZCS is difficult for voltage source fed bridge converter. Difficult for voltage source fed half bridge converter since they have non-zero current coming out of its pole. Which is between A and N. So it becomes quite difficult. However, there are possibility if the I naught current itself goes to 0 because of the operation of circuit after this particular half bridge, if there is certain circuit where because of the operation of the circuit the current goes to 0, then in that case we will achieve the ZCS during turn off case as well. So in this kind of cases where we have the voltage source converter and we have the constant current, then we will only achieve the ZVS during the turn on instance of one of the switches. However, if the current direction is reverse, then we will see the vice versa case, which means my S1 is goes to soft switching while my S2 is hard switch turn on during whenever these devices are turned on. So it depends upon the direction of current which is coming out of the source. However, there are certain scenarios where we have discontinuous conduction mode. So there again you are turning, your current goes to 0 when you are, and then you are turning off your devices. So you can say we have the ZCS operation during that time. This ZCS is only possible, this thing is possible if during operation of circuit I naught goes to 0. For example, your DCM operation, or you can say that, for example, one of the cases DCM, sometimes during operation of full bridge converters, during that time also these conditions may arrive. So that's what GCS only if. So GCS is difficult to achieve in this kind of system, but ZVS we can easily achieve doing this thing. So in this thing we have particularly understand how the short switching can take place in the half bridge converter, which is the building block of any voltage source fed power converter. We will use this understanding, because in subsequent slide when we will discuss about the pulse width modulation of the full bridge converters and the phase shift modulation of full bridge converter, this understanding of these concepts are essential, which you will be using to understand the concepts going ahead. So, thank you very much for patiently listening to this lecture. Thank you.